Hello everyone and welcome to my session. My name is Frédéric Desbiens and I manage IoT and edge computing programs at the Eclipse Foundation. And today I bring you outside of the cloud with me. So the goal of this presentation is really to show you as Java developers, because this is not an IoT track presentation, this is a Java track presentation. And so the whole point is to show you as a Java developer how you can contribute to building IoT solutions. So about me, since I'm outside my little usual sandbox, so I've been working in IT for about 25 years as a developer, architect, product manager, worked for Oracle, Cisco, Pivotal, etc. I've been involved in Cloud Foundry for a while. I've been coding in Java since the early 2000s, and you know the ultimate proof of that involvement, early involvement with Java, is this incredible Java 1 2007 picture that you see. Although you could doubt it, since you know I have much less hair, so it could have been someone else. Anyway, so now I focus strictly on IoT and Edge, but we've got lots of Java technology involved in there, and obviously I work with the Jakarta EE community and other people that are deeply embedded in the Java ecosystem on a daily basis. All right, so the plan of this presentation is simple. First, I will introduce you to some IoT-specific technologies that maybe you didn't hear about. And those IoT technologies, they have Java implementations that you can leverage, so that's already something you could use. And then we'll have a deeper look at some of those technologies. That's the established players part. And then I will provide you a short introduction to more emerging technologies. And some of them are covered in presentations at EclipseCon, so I will tell you a bit about that as well. All right, so going forward, you know, IoT, what is that exactly? IoT is literally devices with compute power that you deploy in the field, and they are connected typically to sensors or sometimes to something called actuators. So literally, actuators are little things that can interact with the physical world, let's say to unlock a door or to start a robot or something. So IoT is all about the device, and typically that's a constrained device with very little memory, very little compute power. So Java is not necessarily a good fit in that environment. But then there's a huge place for Java, obviously, on the edge side and in the cloud side, as we will see a bit later. And when I hear from developers about IoT, you know, especially beginners in the space, they will often think that they don't need to necessarily learn about IoT specific protocols and tools. Why? Because, for example, if I pick this platform, then it supports multiple protocols. I don't have to go deep on those protocols and tools. You know, the platform supports everything. And some others will say that REST can do everything for them, and that plain TCP is good enough, and that kind of stuff. And in some cases, maybe that's right. But you will see there are definite advantages in leveraging IoT specific tools and platforms. And since many of them have Java implementations, as a Java developer, you can leverage that. And the reason why those IoT specific tools and platforms, and even in an edge computing perspective, the tools specific to that are important, is that essentially an IoT project or an edge computing project is widely different than the typical IT project or even the typical cloud native project. Okay, for example, in IoT, you have absolutely to expect that the network will degrade or fail. So we say Internet of Things, and the I here is for Internet, and that simply means you have a network. You're not necessarily connected to the public Internet, but that network won't be stable. Already in data centers, you know, in theory, we have expectations and qualities of service, and sometimes they are not met. But imagine now you are in the field, you're putting microcontrollers on wind turbines in the middle of nowhere. The network won't be reliable, it will degrade, it will fail, and you have to design the whole solution around that. And obviously, if you're just doing plain TCP or REST, they won't be robust in those kind of situations. Then there's the fact that in IoT and Edge, you optimize for size and power. Power consumption is a very important constraint in IoT, since in many cases, the microcontrollers, the constrained devices you deploy in the field, they will operate on battery power, and you don't want them to replace the battery every 2 months or something like that. It would be too expensive. So sometimes you have expectations that the battery life will be 5 years, 10 years, whatever, and really that brings a different mindset to the developer. And then there's the fact that in most cases for IoT and edge projects, you want to operate in a kind of zero trust environment where every device is potentially seen as a liability or as an attack vector. And once again, if you just do plain cloud native or classical DevOps in those types of environments, then it will be much more difficult for you. All right, so taking a step back, this is the typical IoT architecture that we promote in the context of the Eclipse IoT working group. And as you will see, the constrained device is really just one of the 3 pillars that we've got in this architecture. There are edge devices, whether they are gateways or plain edge servers where you will run AI models or things like that, or any type really of workload in the field. And then there are IoT platforms that are typically in the cloud, but here by cloud, I mean public cloud, private cloud, hybrid, whatever the cloud is for you. Okay, and so Java really fits at the edge and fits in IoT cloud platforms. It's less of a fit on constrained devices. The dream of Java Macro Edition and things like that. Well, it's still around. You can still download it, but really, even with modularity, you cannot target a microcontroller with 256 kilobytes of memory using Java. You will use Python, you will use even embedded Rust or things like that. But unfortunately, Java is not necessarily the language of choice there. Obviously, if you have a few megabytes of memory and all of that, then possibilities open, obviously, through modularity. But the focus of this presentation is rather to show what you can do at the edge and in the IoT cloud platforms with the Java language. And this is a view of where Eclipse projects and technologies fit. And you will see, for examples, in the case of IoT platforms, obviously, Jakarta, MacroProfile, Tamarin for the virtual machines. All of that is taken into consideration into this model. But today, we are focusing on this protocols layer that you see on the slide. And I will talk about a few of the projects that you see in the integration and data categories in IoT cloud platforms. Okay, so let's have a first look at the family of IoT protocols that we will cover in greater depth in this presentation. Each of them has a specific model, specific pros and cons and things like that. But at a very basic level, what you will realize is that those common IoT protocols are each things that live outside of the Eclipse Foundation. So in the case of CoAP, that's an RFC. In the case of DDS, that's managed by the DDS Foundation under the OMG. Lightweight M2M is specified at OMA. OPC UA is its own little, it's a huge thing, right? And MQTT lives at Oasis. And each of them has a different model. So depending on your use case, maybe publish subscribe is a better choice, maybe request response is a better choice. Anyway, so we'll go in great depth on CoAP, DDS, lightweight M2M, and MQTT in this presentation. And in the case of OPC UA, I leave it out because it's been around for a while. And it can be both publish, subscribe, or request response. And in fact, it's got 6 different profiles, and it's a complicated thing. So I'm leaving, I'm trying to avoid it for the time being, since this is an intro level presentation. But certainly, this is a viable option, and we've got an open source implementation. And so, when you look at those industry standard protocols for IoT, you will see that we have Java implementations for most of them at the Eclipse Foundation. For CoAP, that's the Californium project that's literally running. It's been since 2014. For lightweight M2M, we have Leshan, which is both a client and there's a reference server inside it. Eclipse Milo is our OPC UA Java implementation. For MQTT, there is the Eclipse Paho set of client with Java. And then the Eclipse Amlin broker has got some Java implementation. And then or I should say, so in the case of Hamlin, it's got support for some Java technologies. And then there's the emerging SpaPlug protocol. Well, by itself, it's an open source specification at the Eclipse Foundation, like the Jakarta ones. But at the same time, the Eclipse Tahoe implementation has got a Java implementation. So plenty of Java code that you can leverage there, depending on which protocol is the right choice for your project. And in a wider perspective, when you consider all of those choices for protocols, in an IoT perspective, the choice of protocol will impact many things, right? The performance and throughput of your solution, the battery life, your own productivity as you write the code, and obviously the overall security. And there's the fact that HTTP is missing many features that are supported by those protocols, like quality of service, guaranteed reliability, etc. And I will tell you a bit about those features as we cover each of the protocols. But ultimately, the number one reason why you need to pick one of those protocols instead of just plain TCP or plain REST for your IoT project, if you're a Java developer, is really that low-level protocols will slow you down in the literal sense, because most of those protocols offer higher throughputs than plain REST and plain TCP. But at the same time, you will be less productive as a developer because you will need to reinvent the wheel and do unnecessary parsing and things like that. Anyway, so one thing to consider as well is that not only we've got Java implementations for popular protocols, but several of our IoT platforms that run typically at the edge or in the cloud are based on Java. And a good example of that is Eclipse Kura. Eclipse Kura is a completely integrated solution for IoT gateways with support for multiple protocols. And if you need to extend it to add support for additional protocols or to literally deploy IoT applications on them, that's plain Java OSGi package code that you deploy on the gateway. So all of the other projects that you see on the slide are built in Java, and each of them has a specific role to play in a wider IoT architecture. So Ono is very good to handle device connectivity. Ditto is a full-blown platform with APIs to manage digital twins, and you can deploy using Eclipse Hogbit updates to your constrained devices, and all of that is built in Java. So if you deploy those solutions, then obviously they operate using the same rules as the Java applications you already manage. And in some cases, if you need to extend them, then obviously you can do that in Java. So plenty of things to do for a Java developer using those platforms. And if you need to run containers at the edge, you could think that, hey, I will run Kubernetes there and it's easy and I know it and all of that. The problem with Kubernetes or even smaller weight distributions like K3s is that the overall stack is much more fragile than using an edge computing platform that is built from the ground up for the edge. And this is where something like Eclipse ioFog is interesting. So Eclipse ioFog integrates with Kubernetes, but can run in standalone mode. And obviously we support any containers. So you do Quarkus, you do plain Java, you do Wi-Fi Swarm, you compile using GraalVM and put some executable in there. Whatever you do, whatever is the resulting container, you can orchestrate that at the edge using ioFog. And to give you an idea of how lightweight Eclipse ioFog is, okay, Eclipse ioFog can run up to 3 containers on a little board like a Raspberry Pi Zero. Okay, and that is a very constrained environment. So obviously you need to design your microservices inside the containers accordingly, according to the resource constraints that you have on such a small board. But if you write very thrifty code, very efficient code, ioFog is so lightweight that it won't add much to the footprint of whatever you are deploying. So, you wouldn't put K3S in an environment like that. And so ioFog is really a very, very good solution to enable you to run your Java code at the edge. And when I say the edge, it's literally in the field, right? You need this little server to aggregate the data for 20 wind turbines in a specific area, for example. Then you can do that by putting some containers on an ioFog node, for example. Okay, so now let's have a deeper look at what CoAP, DDS, MQTT, and Lightweight M2M can do. So CoAP, as I mentioned previously, is a specialized protocol for constrained device, and it's documented in a specific RFC. You have the link on the slide. Really, the main quality of CoAP is that really it runs on minimal overhead and can support any device that will support UDP or an equivalent to UDP. And it can be used to network together devices on the same network, or network between a specific local network and the public internet, or even link together remote devices over the public internet as well. And it's really close in its design to HTTP. So that's a request and response model with the same verbs as REST. And it supports URIs, response codes, MIME types, multicast, etc. So it's very close to HTTP. But the main difference is that all of the headers in CoAP are in binary. So they are not text. So this obviously reduces the footprint of the messages. CoAP by nature is asynchronous and low overhead. It's very simple to parse and comes with the built-in facilities to parse both the headers and the content of the messages in a binary fashion. And one nice thing about it is that it offers you like HTTP proxy and caching capabilities if you have the infrastructure for that in your environment. So this is the protocol stack for CoAP. And as you can see, one interesting thing about it is that it can even run over Bluetooth. So you see Bluetooth low energy WPAN just above the physical channel, okay? And over that 6LoWPAN, so that's an implementation of IPv6 primitives on the top of Bluetooth. So you can use that in order to connect to your device out of the box with when you are using CoAP. And so that's certainly a very attractive proposition. So Eclipse Californium as a CoAP implementation implements a whole slew of features that are documented in additional RFCs. And as a reference, I put that on the slide. One interesting thing is that there's even CoAP to HTTP cross-proxy support in there. So you can bridge HTTP and CoAP environments together without any problem. Californium, by the way, I should say that is both a client implementation and a server implementation, so you can use it in either mode, and it's fully, fully in Java. DDS now. DDS is really a machine-to-machine publish subscribe protocol, and when we say machine-to-machine, it's really that you are building meshes with the protocol. So any node can be a publisher, a subscriber, or both simultaneously. And it's popular in many verticals right now, like aerospace, defense, air traffic control, robotics. And the specification lives under the DDS Foundation, which is a subcomponent of the OMG. One interesting twist about DDS is that it provides a kind of a data space. Okay, so it provides spatial and temporal decoupling. So all of the nodes speak to that global shared data space inside the single mesh, and it's completely decentralized. So there's no broker, there's no connection missing or anything like that in the case of DDS. Whatever nodes are in the mesh will receive the traffic. There are quality of service policies, okay, where you can express temporal and availability constraints in there, and it comes with built-in dynamic discovery. This is the stack for DDS, so it can run on the top of UDP or TCP. The problem, however, is that DDS doesn't route well over the public internet. So typically, you will run that in your own distinct networks or private networks, but not so much over the public internet. Whereas in the case of CoAP, you can run over the public internet. However, you can encapsulate DDS traffic using something like Zeno, which is something we'll cover at the end of the presentation. Unfortunately, our implementation for DDS at the Eclipse Foundation is not in Java, it's pure C, but I wanted to cover DDS since it's certainly a viable option there. And it's Cyclone DDS is the default middleware in the ROS2 robot operating system. So that's something that you should know about. Obviously, there are options in the market to integrate with DDS in a Java environment. But anyway, for the sake of completeness, I left DDS in the presentation. But unfortunately, at this point, we don't have a Java implementation at Eclipse. Now, focusing on lightweight M2M. Lightweight M2M builds on the top of CoAP. So everything that I said about CoAP is true for lightweight M2M, but really it's a higher level protocol designed for sensor networks and machine-to-machine environments, okay? And so it defines an extensible resource and data model, which means essentially when you go read the spec and related documents about lightweight M2M, you have already a specific hierarchy, let's say for a temperature sensor, for a pressure sensor or air quality sensor, etc. So all those things are defined, but you can extend the model and implement your own things if you're doing special things. Okay, and lightweight M2M offers many value-added features compared to plain CoAP. For example, it will support device bootstrapping, device configuration. It will take charge of firmware updates, configuration and control, reporting, etc. So lots of added value in there. And the other nice thing about lightweight M2M, since it runs on the top of CoAP, you know, it will support everything that CoAP does, and then some more, in the sense that there's SMS support, for example, so you can do lightweight M2M over SMS as a transport, for example, and there are other options that are available in there. We have two implementations of lightweight M2M at the Eclipse Foundation. First is Leshan. Leshan is really a library for implementing clients and servers. Okay, so it's very simple. It's not using any third-party framework or anything like that. It has very few dependencies, but it comes with a web UI to discover your devices on the network and test. And you build it doing just MVN install, so that's quite standard. And it's based on Eclipse Californium that I told you about earlier. So Leshan is really something that you leverage to build your own client or to add lightweight M2M to your server-side application, okay? But it comes with reference client and servers implementations that you can have a look at. They are not enterprise ready, let's say, but certainly they are a good starting point to learn about the framework or just kick the tires on the protocol. And we've got a pure C client implementation of lightweight M2M in the Wakama project as well. So put that on the slide for the sake of completeness there. Okay, now MQTT. MQTT, last but not least, is a protocol that runs over TCP and targets power-constrained devices over low bandwidth network. Okay, and initially it was in the SCADA market, so industrial automation, if I simplify. But the interesting twist now is that there's something called MQTT SN, which is you could say a parallel version of MQTT, but targeted at UDP, and UDP is well liked in IoT circles because it's lighter weight on bandwidth, it's lighter weight on obviously battery or energy consumption. So MQTT is a publish and subscribe protocol, and you have to remember there that you know, when you talk about IoT and publish and subscribe protocols, this is not meant for durable and persistent messages. So you publish something there with the intent that anyone that needs the information will consume it, will subscribe to the message, but you don't leave the messages for days and days on the broker or anything like that. And so MQTT is a specification that lives at Oasis. MQTT offers 3 different quality of service. So you can request that a message is delivered at most once, at least once, or exactly once. And already you see that that would be a whole mess to implement using REST. It offers persistent sessions, retained messages, last will, and testament. So a message that a device will send before disconnecting from the network. And you can even keep those connections alive using MQTT Keep Alive over the long term. So this is the stack, and you see that for TCP, there's plain MQTT. For UDP, you've got MQTT SN. Now, Eclipse Mosquito and Eclipse Paho are the main implementations we have for MQTT. Eclipse Paho is a collection of MQTT clients, and one of them, and probably the most mature of them, is the Java implementation, and it offers a very wide feature set. So please have a look if you're interested in MQTT. And so as a broker, there is Eclipse Mosquito, which is a very popular broker written in C. Now, we have another option that I forgot to add to this particular slide, which is Eclipse Amlon. So Eclipse Amlon is another broker that we recently obtained. That was recently contributed to the Eclipse Foundation by IBM. So that's another option. Mosquito is very, very lightweight. Amlon implements high availability, clustering, and things like that. So it's a higher level option, certainly a bit heavier on resources, although you can cut it to size up to a point as well. Anyway, so Mosquito and Amlon are your choices of brokers. And as a Java developer, you use the Java version of the Paho MQTT client in order to integrate with that. So emerging challengers now, SpaPlug and Zeno. So we have our own protocols that we manage ourselves at the Eclipse Foundation. And the intent is to tease you a bit about what they can do. So first is SpaPlug. SpaPlug is a protocol that runs on the top of MQTT. MQTT is, how would I say that? A great protocol, very mature, 20 plus years of existence. The good thing about MQTT is that it's very flexible because the MQTT spec doesn't, the MQTT spec doesn't specify anything about the message payloads. So you can put anything in there. The bad thing about MQTT is that, well, unfortunately, it doesn't say anything about the payloads, which means out of the box, you have, let's say, devices like robots and things like that that speak MQTT, and then you have your software that speaks MQTT, but they cannot interoperate out of the box. You have to configure them so that they know where to publish, where to subscribe, and obviously you need to massage the payloads at one end or another, and it's a whole mess. So SpaPlug is trying to solve that by essentially defining standard payloads, standard topic structures, and stateful session management on the top of MQTT. And that's an open source specification that lives at the Eclipse Foundation, like the Jakarta EE specs. And obviously anyone can contribute to that. And the implementation for SpaPlug that we have with a Java implementation is in the Eclipse Tahu project. So please have a look if you're curious and want to solve the interoperability problem around MQTT. And then there's also Zeno. There's a talk a bit later today on Zeno in the IoT track, if you're curious about it. And essentially, Zeno is a pub/sub protocol with very low overhead that integrates the notions of distributed storage, distributed queries, and distributed computations. So really, it's a very clever idea. And out of the box, Zeno is coded in Rust, but it comes with a Java library to integrate with the protocol. So you can leverage that once again as a Java developer to integrate with Zeno infrastructure. And Zeno can encapsulate DDS traffic and eventually other protocols as well. So it's very good for that. So ultimately, how would you pick one of those protocols, or maybe more than one, depending on your use cases? it all boils down to three things. First, your use case. Are you controlling data or controlling devices? If you're collecting data, maybe publish subscribe is better. Maybe if you're controlling devices like a light switch or something, maybe a request response protocol is more appropriate. So sometimes you will implement more than one protocol depending of what you're trying to achieve. Then obviously there are the constraints. How limited will be your bandwidth? What's the size of your battery? How limited is the system on the chip or the little microcontroller that you are using, etc. So the constraints will orient you towards one protocol over the other. And finally, there's the support, literally. So do you have, for the specific hardware that you are targeting, especially for the microcontroller, do you have an implementation of the specific protocol that you are targeting? Does it support the real-time OS you will put on the microcontroller? Can you procure sensors and devices that will support it? And then ultimately, are you comfortable with the Java implementation for the protocol that's available at Eclipse or elsewhere? So that's about it for the main presentation. And now I will have a look at the questions in the chat and try to answer them in a timely fashion. So first question, Java is a typical choice for gateway devices or cloud IoT platforms, but how it can help for edge devices like constrained Cortex microcontrollers, though we have a Java runtime environment, say for Cortex M. And the answer to that is unfortunately not out of the box. I mean, Cortex M environments, let's say like another fruit feather type of environment or things like that, they don't have enough resources to run the GRE. You obviously, through modularity, cut the GRE to size and try to fit it, but you would need at least a few megabytes of memory for that to work. And then there's the full problem of the specific support on the chip for the features that the GRE would be expecting to work, like some system on the chips or some microcontrollers will lack floating point hardware implementations and things like that, and so it makes them less desirable for that kind of stuff. So typically, Java is not necessarily a good choice for microcontroller types of environment. You're better using MicroPython or something like that. However, there are some companies in the market that are trying to cut the GRE even further in order to fit, because as an evolutionary platform, Java Micro Edition that was there in the past is now a dead end, unfortunately. Question number 2, can DDS still work with over routers somehow? Not really well, and that's why essentially the people that work in the DDS space either don't route the traffic over the public internet, or if they do it, they will encapsulate the traffic in something like Zenoh, which is completely possible. And a good example of that is what they did during something called the Indy Autonomous Challenge last weekend. So those were autonomous cars, Indy class cars in where they run the 500 miles of Indianapolis in the US, and they were self-driving cars that were programmed by students essentially. And so they were using DDS on the car itself, but then encapsulating some of that traffic for telemetry in Zenoh and sending that back to the garages. And that's how you will handle it properly. So unfortunately, DDS is not a good fit if you need to route over the public internet. And I'm told that we are out of time, so I will take the time to answer the other questions in the chat after the end of the session, or please feel free to connect with me on SwapCard, and I'll be happy to have a private chat with you to explore whatever concerns you have. In any case, thank you so much for watching today. I hope that, dear Java developers, now you have an idea how you can work at least partly on IoT projects. And looking forward to see you around in our Eclipse IoT and Edge Native and SpaPlug working groups. You are always welcome. So thank you for watching once again, and have a fantastic EclipseCon.